Good morning, everyone. This is Sravanthi. I'm from Department of Aeronautical Engineering. So today we will be studying another topic in the flight vehicle design first module, that is a selection of the airfoil. It's different types of airfoils and their airfoil families and its nomenclature. Airfoil selection. So the airfoil is the heart of the airplane because I have to design or select how I want the airfoil to be. Only then I could get what are the different characteristics I am aiming in that particular airplane, right? So therefore, for that, the important selection or designing an airfoil is very important, and we are going to consider certain parameters or certain different ways or how I expect an airfoil to be, then only I can go and completely say that yes, this particular airfoil is good enough or the design is good enough such that it is giving a good lift or what are the parameters, right? So therefore, the airfoil is the heart of the airplane, right? Then while selecting the airfoil, the first thing that I want to see is that CL by CD should be maximum, right? Only if my CL by CD is maximum, then I'm going to get a good amount of lift, right? So the airfoil is going to affect certain parameters. So we consider certain parameters in a particular designing or selection of an airfoil, which are going to affect it, right? So one is your cruise speed, right? Then the other is your takeoff and landing distances, and the third is the stalling speed, and the fourth is handling qualities, especially if you're talking near the stall. Then finally, it is the overall aerodynamic efficiency during all different phases of the flight, right? Now, all different phases of the flight, this we have seen the different phases of the flight, the mission profile of it. So, therefore, my airfoil is going to be dependent on certain parameters, which in turn would give a proper design, a good enough amount, a good enough aircraft, right? So, depending on the speed, depending on the landing and takeoff distances, stall speed, handling qualities, and its overall efficiency, right? So, the first one is the cruise speed. So, in the cruise speed, we are expecting the aircraft to fly at a minimum drag, right? Right? Why minimum drag? If my drag is minimum only, then I expect that lift. I'm going to get a good lift over there. So therefore, the first and foremost is the aircraft to fly at a D minimum, right? Because why? Because the drag characteristics are going to vary, right? It is going to have different variation with respect to different types, right? So different types with respect to subsonic, with respect to supersonic, it is going to vary. So therefore, when I am looking in designing of an airfoil, then I would look into its cruise speed, and cruise speed again dependent on its minimum drag or D minimum, right? So therefore, drag is going to vary. So therefore, it's very important for me to check that particular parameter, right? So the second one is the takeoff and landing distances, right? So when we are calculating the takeoff and landing distances, right, I want the speed, the V takeoff or V landing distances to be very lower, almost equal to 1.25 V stall, right? So your V takeoff or V landing to be very almost or equal to 1.25 of V stall, right? And we also know so V stall is something 2W by rho S CL by CV, something like that, right? So now this particular is going to be now my stalling speed and my CL, the parameters are inversely proportional to it. Then therefore, if only I can decrease the stalling speed, then I should be able to increase my CL max here, which is what I want, right? So therefore, I keep the stalling speeds to be minimum here, and also therefore the takeoff speed and the landing speed to be much lower, almost equal to its 1.25 V stall. And if these are low, then VS is going to be low. If VS is low for a given thrust to weight ratio, then your takeoff and landing distance are also going to be low, and therefore from the equation, we know that CL is going to increase, which is what is expected at the end, right? So then is the stalling speed, right? Now, as we have seen in that equation, if I could keep the V stall to be very much less, only then my CL is going to be higher as possible, right? Then the handling qualities of all of them, like the performance of the airplane is important, right? So therefore, I check all the different categories or different variations at every different point of the airplane, or airfoil, right? So therefore it is going to depend, and that performance is going to be depend on my efficiency of the aircraft or efficiency of the airfoil or wing, whatever it is, right? Now again, your efficiency is dependent on CL or it is dependent on CL by CD, right? So therefore CL by CD should be a maximum number or CL should be a maximum here, right? So only then I could say that yes, my efficiency of a particular airfoil or efficiency of a particular aircraft is achieved to be a good one, right? So these are the different parameters that are going to be affected or that we are going to consider when we are selecting or a designer is going to design an airfoil, right? The first is speed, second is takeoff and landing distances, then it is stalling speed or stall angle, right? Then all the handling qualities and the overall efficiency of the aircraft or airfoil, right? So then it is a airfoil geometry, right? So in the airfoil geometry, an airfoil is a 2D cross section of a lifting surface, right? So airfoils, I have different type of airfoils, right? NACA series, and then there are other airfoils, right? So airfoils use streamlined shapes to produce a lift with a low drag, right? I want more amount of lift with less amount of drag to be generated in it. So therefore, how that is how my airfoil shape is going to be designed, correct? So here we can see, and so therefore, if I there could be symmetric or a cambered airfoil, right? Then the nomenclature, if we see, I'm sure this we have studied it in the previous semesters, but just a glimpse of it's been given here because we need to go and finally do certain numericals or estimate certain values. So therefore, we'll just take it one more time, right? So therefore, use a streamline shapes to produce a lift with low drag, right? Then the leading edges and trailing edges, we know the beginning point to the ending point, right? So the leading edge of the airfoil is the forwardmost point, where the trailing edges is the after point. So leading edge and the trailing edge, right? Then the chord line is a straight line that's connecting the leading and trailing edge, right? So the chord line is going to be a straight one between your leadings and trailings, right? Its length is called its chord length, or you can just simply say it as a C, or it is just a chord, right? So again, and it is very difficult for me to have a perfect shape trailing edge, right? So therefore, I cannot always be a designer cannot always have a perfect shape trailing edge. So therefore, the most of their foils have a blunt trailing edge with a small finite thickness in it, right? Then there is a camber. So camber refers to the curvature characteristics of the most airfoil. So from here we can see, right? Camber is the most curvature characteristics. Then the mean camber line is the line equidistant from the upper and the lower surfaces, right? So then the total airfoil camber can be defined here from that. Total airfoil camber is defined as the maximum distance of the mean camber line from the chord line, right? Is expressed as a percentage of the chord. Okay. Then and also airfoil with a concave lower surfaces are known as under cambered airfoil here. So camber line is going to be scaled to produce a desired maximum camber. Then the other term is your local thickness or thickness to chord ratio, right? So the local thickness is the distance between your upper and lower surfaces. So maximum thickness is simply referred as airfoil thickness, we can say, or thickness to T by C also we can write it here. Thickness to chord ratio. Then thickness to chord ratio is usually between 8 to 14. It is a typical thickness that you are expecting. 8 to 14 or 8, 9, 10, 12 is a moderate thickness, right? Then going to airfoil families, right? So the shape of the airfoil can be described in many ways, right? So here we have a NACA series. So here we are going to talk about a NACA series, right? In NACA series, we will be seeing a NACA 4 series, 5 series, and a 6 series, right? So NACA 4 series airfoil is defined by one for a thickness and one for camber that are parameterized by 4 digits, right? An example, we'll just take an example and we'll see how or what are these digits exactly saying us, right? So a NACA 2412, if we take the first digit, right? The first digit we have 2412, right? So last two digits are your thickness, second is the camber, right? The maximum camber, and the first defines the first, you define the maximum camber as a percentage of the chord, right? 2%, right? It is defining the location of the maximum camber in tens of the chord, so it is 0.4, right? Then the last two digits, 12. 12 is the thickness of the airfoil in a percent chord. T by C is going to be 0.12. Okay, so that is what my NACA 4 series is designating me, and yeah, it is also shown here. So NACA 2412. Okay, first digit camber, second is the location of it, and the final two digits are going to be the T by C over here, right? So if a NACA series is something like this, then it is a symmetric section. We have a symmetric and unsymmetric, or symmetric and camber airfoil, right? Then we will go to NACA 23012. It's a 5-digit series, right? So what we just saw was a 4-digit series. Then here we have a NACA 5-digit series saying 23012, right? 23012. If we take, so if the first one, right? So the first one, if we consider the 3 by 2 first digit is the designing CL in the tens of it, right? 3 by 2 by is going to give you the design CL, right? The next digit gives the location of the maximum camber along the chord from leading edge in hundreds of chord, right? Similarly, if we see that 6-digit series, and it is a laminar type of an airfoil at A is equal to 0.6, and the maximize the region over which the flow is laminar. And the advantage here is, if me taking a 6-digit series is drag over a range of CL can be reduced. I can reduce much of a drag if I am going to have a NACA series of a 6-digit series. Okay, so these are some of the airfoil families that we are discussing in the NACA series only, right? 4-digit, 5-digit, and 6-digit series. Then the airfoil lift and drag, right? We all know how lift is generated, right? And we also know that how drag should be reduced, right? So an airfoil generates a lift by changing the velocity of the air passing over and under itself, right? Bernoulli's equation, right? So Bernoulli's equation shows that higher velocities produce lower pressures, right? So when I have a higher velocity, it is going to give me a very low pressure. Why? Because my altitudes are increasing, then the pressure is going to really come down. So the upper surface of the airfoil tends to be pulled upward by lower than the ambient pressure, while the lower surface of the airfoil tends to be pushed upward by higher than an ambient pressure. Right? The difference of it will generate the net amount of the lift. Okay, so the all two-dimensional airfoil drag is produced by, so we again, when we're talking about the drag, we have different types of drags that we will be seeing in the next further classes, but it is already finished, right? We have already studied the drag configuration in the previous semesters, but if possible, let us also see one more time in this flight vehicle design subject, right? All two-dimensional airfoil drag is produced by skin friction and the pressure effects, right? So these are again resulting from the flow separation and shocks. Again, flow separation means if that again is depending on my airfoil shape. If the flow is accelerating more, right, in this direction, right? So how the flow is accelerating, or the angle of attacks, or the CL, or the speed of it, accordingly I will have a flow separation, or I might have a flow that is going to be separated and is going to reattach again. But depending again on all the different parameters, I have a maybe my flow is going to be separated, and there are shocks. Okay, now in a 3D, right? In three-dimensional flow, the drag due to lift is produced, right? So the airfoil selection of lift, drag, and pitching moment are defined in non-dimensional forms here, right? So non-dimensional forms, if we talk CL, CD, and CM, so that is a lift coefficient, drag coefficient, and pitching moment coefficient. But we know lift half rho v square SCL. From there itself, I'm just writing it in non-dimensional form. Drag half rho v square SCD. Okay. So lift force is perpendicular to the flight direction, while the drag force is parallel. So all these things we know how the different forces acting on the body, right? Lift is perpendicular to the flight direction, and drag is again parallel to it, right? So this is what CL, CD, CM, right? Half rho L is what? Half rho V square is CL, right? Half rho V square is again a dynamic pressure, so we can express half rho v square, not in terms of density or in terms of speed. We can directly write in terms of a dynamic pressure over there, Q, which is Q. Okay. So alpha we know angle of attack, right? So CL is going to be a section lift by QC. CD is going to be a section drag by QC. CM is again a section moment by QC square, right? So the point about which the pitching moment remains constant for any angle of attack is called aerodynamic center, right? The aerodynamic center is not same as the airfoil center of the pressure or lift, right? The center of pressure is behind the aerodynamic center. Then stall, right? Now stall is very important during airfoil selection, because if what is it we have said in the factors affecting, we said that cruise speed is important, stalling angle or stall speed is also important, right? If only I have a lesser stall angle, only then I should be able to increase my CL here, right? So because at the end I'm expecting CL to be more or CL by CD, right, to be a maximum, right? So therefore, all this to be attained, all I want is VS to be more, right? I don't want stall to be too much, right? So therefore, while designing or while selecting an airfoil, select an airfoil in such a way that all your conditions are going to be satisfied, right? So as now in your stall, if we see a stall separately, then as my angle of attack is increasing, flow starts to separate from the surface. But again, that is what we have said, right? So if I just consider it, depending on my angle of attack, my maybe the flow is accelerating good, right? So then depending on the angle of attack, you might have that separation, right? So again, this is again two different types of airfoils, actin or velatin airfoils, right? So as your angle of attack is keep on changing, right? It is increasing, flow starts to separate, right? Flow starting to separate, but again it is getting reattached, right? But maybe a flow again separates and is not going to reattach at any point of time, right? So therefore, as angle of attack is increases, flow start to separate from the surface, but it gets reattached. But at some higher angle of attack, the flow is going to fail to reattach itself, right? Which immediately stalls the entire airfoil, right? So I don't want that condition to happen here, right? So because this causes a change in the lift or changes in your pitching moments. Then the types of airfoil, right? So types of airfoil could be fat, thin, or very thin airfoils, right? So the fat airfoils, if you see the round leading edges, right? So right, so the round leading edges and the thickness to chord ratio is to be greater than 14% here, right? So stall from the trailing edge. The turbulent boundary layer increases with increase in the angle of attack, and around 10 degree you expect it to separate starting at the trailing edge. So here it is going to separate from trailing edge to leading edge, whereas in a thin air foils, the flow is going to separate from leading edge to trailing edges. Okay, so at around 10 degree, the boundary layer begins to separate, starting at trailing edge and moving forward as the angle of attack is further increased and the loss of lift is gradual. So whereas for thin airfoil stall, it going to stall from the leading edge only. So for thin, it is going to be leading to trailing. Okay, so thinner airfoil starts to stall from a leading edge, and if the airfoil is of a moderate thickness, so thickness it is going to be a 6 to 14% of it, and usually if it is 8 or 9 to 10%, if it is 8 to 10 or 12 or 9 to 20, 10 or 12, it is going to be a moderate thickness here, right? So at small angle, flow separates, it reattaches, right? It can reattach, but again, as it is keep on increasing, the flow is going to separate, and again the flow is not going to reattach itself. So now when we are looking into a design perspective, right now all these we are seeing the selection of airfoil or the how I want or how the designer is going to design the airfoil should come to a conclusion where I want a better airfoil or I want an airfoil good enough such that my characteristics are going to be enhanced, right? What characteristics are we going talking about? Either lift to be increased or drag to be a minimum one, or CL by CD to be a maximum, or CL to be an increasing number, or stall effect to be gradually little less, right? So I consider all of these conditions and I design such type of airfoil, or I select the type of airfoil according to the mission or according to the application of it. right? So therefore, if we just say that is according to design perspective, then my CL is going to be a function of different things, a function of maybe a Reynolds number if you're talking about, if maybe it is an angle of attack or if it is a Mach number. So if we are talking now according to this angle of attack or Mach number we have seen, right? Now if we are talking specifically about the Reynolds number, right? My CL and CD are going to vary with respect to Reynolds number, right? Now what is your Reynolds number? Reynolds number we know, inviscid to viscid flows, right? Inviscid to viscid flows or rho VL by mu UD or mu, right? So therefore, now what is happening? We are saying that I want to have a better CL or I want to have a better CL by CD, and whereas I am dependent on a particular Reynolds number, then I also have to see what exactly is happening with the Reynolds number. I could have a laminar flow or I could have a turbulent flow. If I have a turbulent flow, then it is going to be a little degraded one, right? Now, so as my altitudes are increasing, now what is happening? If you are keep on raising, right? When you are raising the altitudes, my density is going to change definitely, right? But your viscosity is going to be a constant number only, right? So as density is decreasing, your Reynolds number also changes. If my density is decreasing, my Reynolds number changes. If my Reynolds number changes, then my CL by CD also changes, right? So therefore, while selecting an airfoil, we consider all these different parameters or check all the different characteristics and then choose that particular airfoil, right? So therefore, select the airfoil such that it is good enough with respect to different parameters, right? Different parameters could be Reynolds number, could be in terms of altitude, could be in terms of cruise speed condition, or could be in terms of CL or CL by CD or anything, right? So that is how I go and select the airfoil. Okay, so in the next class we will be seeing about the wing and the tail. Okay, so that is all for today. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.